And we were good. So good afternoon, everybody, and welcome to today's webinar regarding uh, kinematic and dynamic motion analysis within Creo, which is also reached through an extension called the Mechanism Dynamics Extension, MDO. And today, Andrea Francis from the Virtual Center of Excellence is going to give us a review on the capabilities of this extension and also give us a demo. So this is going to be a little bit of a longer one today. We're looking probably about 30 minutes, maybe 35. But we will handle any and all questions that you have. Please type those into the Q&A box, and we'll try to answer those as we go, but we'll definitely answer them at the end. So Andrea, thank you very much for helping us out today. The VCOE is a fantastic resource for our clients and also for us at 3HTI with our customers using PTC. So thank you very much and take it away.
Thanks, Rob. And hello, everyone. Welcome to this webinar. I'm Andrea, as Rob said. I will be walking you through mechanism design, mechanism dynamics, kinematics analysis, all of those. We're going to go over them today. And if we think about why you would even start looking into this subject, really, if you have designs, maybe some of the products that you work with, they have components that are fixed, they're non-moving components, but maybe some portion of them or maybe a majority of them have motion into them. You want to be able to take into account that movement. How do the parts move? How do they fit together? How do they interact with each other? And that in and of itself adds a layer of complexity to your design. You have to take that into account, whether it's just piecing together the components or even achieving certain requirements that you have to take that into account. And the regular methodologies of just assembling in your parts, putting them together with fixed constraints won't do for that because it doesn't reflect how these parts are going to move out in the real world. Do you want to have that movement, whether it's the part or an assembly? If you have a pendulum, a slider, things like that, you want to have those be considered into your design. You'd maybe want to explore the kinematic behavior, the dynamic behavior. How does this part move when it's being considered? Do you really, are you designing it properly? Is there something else that you need to add? Do you also use prototypes maybe to test things out of, hey, is this going to collide with something? Is it going to move to the exact range that we designed it for? And you don't want to just get a part that works fine. You want to get to the most optimum or to the best possible design that you can get. And really, that's where you would start considering mechanism design, putting in components that move into your CAD design, and then even taking it a step further and then analyzing it. And that's what we're able to do inside of Creo. We really have multiple different extensions that allow you to do that. And we're going to be focusing on two for today and mostly on the dynamic side of things. But if you're looking to just define mechanisms, perform a bit of motion analysis on them, Creo Mechanism Design Extension, or MDX for short, is the one that's going to allow you to do that. Mechanism Dynamics Extension, or MDO for short, is the one that allows you to create your kinematic or dynamic simulation or the behavior of your product out into your CAD system. And if we start just focusing on the first one, MDX, this is going to be where you're going in and defining in how everything is structured out. You're defining how your parts are going to move, if you have rotations, if you have pins, bearings, and if you want to perform some motion analysis on it, if you want to examine that mechanism. For example, you have a simple motor, you want to see how it's driving in your parts over a given period of time. That's where you're able to do it. And it's a great extension because, first of all, it's integrated inside of Creo. You're working within your port environment or your assembly environment, depending on what it is that you're working on. And then you can really dynamically work on to dragging in your parts. Let's say you have your gears on here, you want to drag them around, see from left to right how they're spinning, how they're moving, you're able to do that. And then take it a step further. Do you care about any interferences? If you have a model, if you're putting it in its full range of motion and you want to find out problems before you even start going into production or even prototyping for it, if it's swinging from one side, does it collide with another part? Does it get stuck in one place? Are you working from the design side of things and designing around a mechanism as well, where you'd want to see the area of, oh, this is where there's going to be movement, so I shouldn't design into that area, but I want to design around that. So you'd want to see the extent of that movement or the envelope. We also have those capabilities. Or you want to do a trace curves, you see exactly where the path of the movement is, how it's going to move around, turn, spin, slide, what is the limitation of that movement. You're also able to see that today. And then those save those configurations. You can have all of those information saved within your assembly of your product. And that's it for MDX. If we take a look more on the side of dynamics, if we're looking at MDO specifically, this is going to be where you're going in and creating your simulations. You have your forces that you want to consider, accelerations, you have additional constraints that you want to consider. All of those for your moving parts, you can have those simulated and really explore the real world behavior of your system. Do you want to work with gravity, springs, dampers, friction, contacts? If let's say you have a spring defined between 2 points, you know its strength, you know its size, you can have even the system understand how that spring works, the idea of maybe a stored force or a released force, and then run an analysis based. You can run kinematic analysis, looking at position, velocity, acceleration of the parts that you have, dynamic motion analysis as well, adding in components like friction, gravity, forces. It could be a really simple design, but when you're adding in those motion, it could get really complex. You have to take into account the force of gravity. If you have, let's say, spring on the arms, like what we have on the screen right now, you have to take into account that. If you have friction of the ball as it rolls over, it could get pretty complex the more you add motion to it, and you're able to understand and calculate for that with mechanism dynamics extension. For the results themselves, you have options of how you can take a look at your information. You can measure or even graph your specifications. You care about velocity at, for example, a specific joint onto your pendulum, or maybe a reaction forces of loads, torques that you have. And then do you want to share out that information with others? Do you want to create reports like having graphs or table information, or do you want to share it out in forms of animation so even show them how the part or the product is going to move? And then with that, you can even integrate well with other solutions in Creo. Let's say that you've already analyzed the behavior of that mechanism. You want to perform a structural analysis onto one of the components, understand the stresses, the displacement. You can work with a tool like Creo Simulate, for example, and already bring in the forces from Creo Mechanism Dynamics, and then bring it into your structural analysis setup to run it from there. If you want to, for example, look at the behavior of your model, let's say you have a limit of your force onto that part, you know that upper threshold. How thick should your part be, or even how thin can you make it while still maintaining a certain safety factor? You can look at that in terms of the behavior. And then calculations. Are you performing calculations? Do you want to bring in the information and utilize it for additional information that you need? You have options on how you would want that. I've had a customer recently as well that I've worked with where they wanted to incorporate mechanisms with ergonomics. They're really looking at how the product that they're working on is going to interact with mannequin models. And you can definitely work with that as well within Creo. So it's really all about optimizing your product, looking at analysis in various different ways. And that's it in terms of the slides that I wanted to go over. Let's actually jump into a demonstration to see how all of this works out. And we're going to be actually working on this air turbine assembly. Basically, we have our air turbine over here. It pops off on the outside or on the side of it of the aircraft, and it will provide some sort of emergency or auxiliary air in different situations. But we're going to be focusing on different parts of it and building out actually different mechanisms inside of that assembly. And one thing to know is when you're working on a product, maybe you have a simple product with just a simple mechanism, but it could be a very simple product with multiple different mechanisms involved that make it move, make it work. And you can incorporate all of those within assembly, sub-assembly is a top level assembly, depending on how you would want them structured. And we're going to start here. In our case, let's say that we're starting on to one of the linkages on that turbine. And for that linkage in and of itself, it's a hydraulic dampening linkage. Traditionally, how you would assemble this if you're not considering mechanisms is you would do like a coincident in the middle, align maybe the flats together, even align the outside. And what this means is that you have all of these parts stuck together. You may be able to even put some distance to it. Let's say that you're putting it into an opening position, a fully open position, or some sort of angle to it as well. You can define this, but that's not really what it's going to be in the real world. That's not going to be how the product itself is going to work. And that's where you'd bring in mechanisms into this. You can apply, for example, a slider. That's how we're going to have our linkage move. We can have um, all of the constraints for that slider set up. We can have it centered in, aligned properly. We can even apply a translation constraint to it and then have it move as if it's our slider joint inside of Creo. If we want to take a look at how it works, we can even drag in those components around. Let's say we're picking onto that part. I can drag it, move it back and forth, and then you can see everything moves with it. It's moving properly, exactly to where I want it to be. But here it doesn't have any limits to it. What you can do as well is you can still go in and put limits onto those constraints. If you have a minimum or a maximum limit that you know of, this is within the boundary or the range that is going to move in, you can put those in, and then it understands it properly onto your model. So if I move it back around, you can see we have those limits properly in place. And that's one way to start defining your linkages. If let's say onto our linkage here, we have our clevis up on top, it also has some sort of movement into it. And traditionally, how we would assemble this is we would have it fixed in a couple of coincidence, maybe onto our pins, but that's not what we want. So we can go in and remove those previous constraints that we have and then apply our proper mechanisms. And you can see here in the top left, you have options on what it is that you can define. You can, let's say, define a pin, a slider, a cylinder, planar movement, balls, bearings, for example. You really have a lot of choices depending on the type of system or the structure that we have. But in my case, I just have a pin joint and I can go in, put it in properly. I can just have it coincide, having it, even adding in a translation constraint on here and just making sure that nothing goes out of bounds. And that's it. I really have my pin joint properly in place. And as I move it around, it even interacts with the other linkage that we created and they move seamlessly together as they should. If you actually take a look at how that looks within our larger assembly, now we can drag up our air turbine around and we have it able to open now. We can see the linkage itself moves properly, all of the components move, and we have started building out the start of how this whole thing is going to work. Now you can also work with snapshots within Creo. Let's say that you want to save um, a position of your structure, maybe an open position or in a closed position or even part way. It really helps you in different ways, working in different ways. Let's say for today, as an engineer, I'm working with my air turbine in an open position versus an hour later, I need it in a part-way position. For example, it just is easier for you to be able to work within. Right. Okay. And that's the first part. Now let's actually move on to another component involved in this mechanism, and that is our actuator. And here, what we're going to do differently than what we started with is we're going to start putting a lot more intelligence into our model. What you saw previously was the start of defining your mechanisms. It's a bit of a manual process. But now, what if after I've defined my mechanism, I do not want to be the one that drags it in and out manually? I want it to move based on, let's say, a motor or something that's driving it around inside of Creo. So let's take a look at how we can do that. In my case, we're starting with the actuator. It has a slider joint already in place for it. In the mechanism design extension, there's actually a mechanism tree with all of the different conditions and settings that you can apply. These could be motors, it could be springs, dampers, anything that you need to apply to have them be the drivers for your mechanism. In my case, let's say I want a servo motor to be the one that's driving in the slider. So I can go in, apply my motor. Let's say I wanted to move this axis a few millimeters. For example, I get to pick and choose of, hey, is this I'm moving based on position, velocity, acceleration, and then I'm going in specifying my magnitudes. Do I use a constant? Do I use a ramp sort of magnitude? And then I could just add it in on here, and then that will be what is helping us move that part. So for us to move it, I would run my analysis. After I've defined my servo, I'm going in and in my analysis, setting it up, let's say over a given time frame with that specific servo that I'm working with, I want to run an analysis on this action. And once we run it, it moves it for us automatically. I'm not the one that's dragging it like what we did before, but instead I'm seeing it how it would be working with my servo. This way could help you identify any issues. Let's say if you're analyzing it as well in the larger assembly, which we'll see as well a bit later, but we're really able to see what's going to happen onto our structure. We can do a few things as well from there. Let's say with the analysis, I wanted to play back. It could be an animation. I can speed it up, slow it down, do whatever I want with it. And then I can even export it out to, let's say, movie files, share it out to others as well if I need to, just to show them what's going on with the product. I can even do measurements. Let's say I want the offset from pin to pin as this is moving throughout the given time frame that I have for it. I can run a measurement exactly onto the specifications of the analysis, and then it will graph me my measurement, let's say for my position, over that given time frame that I have for it. And that's just on the part itself here. I can work on it as well in the larger assembly. If I'm starting in with my small linkage assembly or sub-assembly, and then I'm moving on to my top level, now I can see how everything is put to motion as well. I don't have to drag it out myself. I can rerun my analysis onto my entire turbine, give it the same my time frame in this case, and then assign in my motor that's going to be my driver, and then have it run for me automatically. And then it moves it out. It's opening up my door in this case, and it seems good. Like my whole structure is moving as it should up until now. You can even perform additional measurements onto all of this. Maybe you care about the position or the angle onto your hinge or on your joint that you're working on. Those are some things that you can also inspect or take a look at from the top level assembly that you're working on. And still graphs you that graph so you can see it starts to open up and then it goes down exactly to how we need it. And all of those just simple situations that we're dealing with up until now. You can involve a lot more complexity with this as well. So you can do something like a cam sort of situation with the slatch that we have. We can set it up. It's really easy to set up. We're just grabbing onto the surfaces of our hook and our pin, and then that is going to be the one that will help us enable liftoff in our case. We need them to separate to open up our entire structure. We can have them pull away, still working in maybe from a bit more of a manual approach to test things out. But then once we're happy with how it looks, we can then set up our analysis for it and then see if we need to make any tweaks, any changes to all of that, or if we need to design this whole thing once again. Nope. In my case, we have our latch going in and around. We probably have to apply a limit to it, but everything else works out fine. The whole structure opens up properly, and we understand what's going on around it. We can do a few things as well from here, like applying a trace curve, for example, have it draw it for us to really see where that pin is moving. That can be something like maybe you're designing other components around it, or you're even designing a slot for it and you really want to see where that motion is. The trace curve could come into play, and then you can even add in the aspect of working with areas and then the envelope to really see what's going on in that given area. And that's everything really in terms of mechanism design itself. If we want to take that design now that we have with our air turbine and actually focus on the dynamics of things or the analysis side of things, it's really important to, when you're doing mechanisms or even when you're creating your products, to take into account the different conditions and the requirements that you have. Usually that comes into the form of forces, friction, dampers, springs, anything that affects the product or drives it to move around. And the mechanism dynamics extension is the one that you're able to use to simulate these various different types of real world behavior for your mechanism. And we can take an example of that as well. If we go back onto that same actuator that we started, we had our servo motor be the driver for our movement onto that actuator. Now, instead of that, let's say that instead of the servo motor, actually that actuator is spring loaded instead. So we can go in and define or set up our spring inside of Creo. We can say from this point to this point, this is where our spring is going to be, and then give it a strength. We know our K factor in this case. And then it will automatically build the spring for us onto our model. And then it builds it out. We're even able to tweak it around, let's say, in terms of size. And then it's not just a static piece that we've built out. Instead, the system or Creo understands that this is a spring and this is how it should move and interact. It can compress, uncompress. You're applying force on here. It really knows what the spring is and should do. And the reason for that is that's how our engine for it is built. You can utilize it inside of your analysis. It understands that, oh, instead of my servo, let's just have it be spring loaded. You can just apply your analysis over, let's say, this given duration, and then it will move according to how the spring should behave. And then this is a simple spring. If you want to add a lot more elements to it, maybe you'd want to consider, let's say, friction or other factors inside of it, maybe limits. You can definitely do that, like having a coefficient of restitution, enabling friction in different directions. You can definitely apply this. But really, if you're looking at the analysis, having it be rerun, then you can see the differences of the ideal spring versus the one with additional factors. And then if you play back just to see how it's going to look, now we can see it's a bit slower. We might have some bumping at the top, but even on our graph as well, once we've measured in that position, we're able to also see how all of this is going to look like, and if it's correct or not, or if we need to make adjustments to. And then finally, this is just working on our small actuator assembly. We can even bring other considerations like the net load, for example. And that could be just onto that actuator itself, still graphing it, understanding it from that perspective, or even taking it onto the top level assembly and seeing how that might affect other parts inside of that assembly in and of itself. So with everything in place, now we have our spring. We can replay or rerun our analysis onto our turbine. And then once we have that, we're going to be able to really work with our different measurements. Still, it's a spring loaded mechanism. We have our latch. All of the components are in place properly. We have our trace. And now we can actually take a look at your forces, maybe graphs of measurements like velocity, position, reaction forces, the net load, for example, impact. You can have those considerations in place. But with the measurements now, once let's say you're measuring in your net load, what it does is, in addition to the graph, it also puts arrows onto the model for you. So once it plays in the analysis or we replay the playback itself, we're going to be able to see how our net loads change over that given period. So we have our graph first, and then if we play it back, we can have it display those arrows for us in the playback. And we're going to see actually how our loads change as our mechanism opens, as it moves, and as time progresses throughout this. So a really good understanding from this point of view of what's happening. Do you need to make changes? Is this above the limitations that you've set? Is it below? Are you good? Do you need to change anything? You're able to consider all of those different point of views from there. And then that's mechanism dynamics extension. You're really able to simulate everything, understand the real world behavior of your structures, of your models. But then once you take a look at that, maybe you want to tie it back to other types of analysis that you run. These could come into the form of a structural analysis, even a thermal analysis, running maybe behavioral types of simulations. You can have that. And an example of that would be, in my case, let's say we'd want to run an Creo simulate structural analysis. What you're able to do is you can take in all of the information from your dynamics analysis and then bring it into your structural analysis. In my case, I have my loads. I can even pick and choose the time frame that I want to bring in. Is it at the start? Is it at the end? Is it the entire thing that I'm bringing in? And then even the information itself. Am I bringing all of the loads? Is there other factors that I want to eliminate or exclude because they're unnecessary for my calculations? You get to pick and choose what goes into your further type of analysis and if you even want to include everything or not. And once you've done that, you can, let's say, open up Creo Simulate, for example. If we're taking in that centerpiece as an example, we can open it back up and then start running our analysis from there. You can see it brings in all of the forces onto the part of the model for you. And then you can load in those information directly from your mechanism and then simply run your analysis. And that's how you would go end to end throughout all of this. You're designing your model, you're putting it into motion, you're applying your loads, and then you're seeing how all of this is going to play out. So if we run in that static analysis, we're going to be able to see other factors like maybe stress, displacements. Do we care about the von Mises stresses? Do we need to change anything? Is this going to be too much for what we've designed? And then really take it all the way. Yeah, that's it in terms of mechanisms themselves. You can really incorporate them into your design process in various different ways. If you're designing any sort of product, it could be vehicles, it could be maybe medical devices, anything that moves really, and you want to be able to design it and analyze it concurrently, you're able to do that right from within Creo. You can find any issues, any interferences, any information. Let's say if your loads are too high, you need to have them be decreased, how you change that. And then even show others how your model or your product is going to look, how it's going to feel like, how is it going to interact with maybe a person if you're working more on the ergonomic side of things. And really eliminate a lot of time maybe that you have wasted or spend a lot of time even trying to understand if what you've designed is correct. If you utilize physical prototypes, there's multiple different ways that you can incorporate that. And really, that's mechanism design. So thank you for joining us. Rob, do you have anything else to go over? Or do we have
Andre,
any questions?
that's it. I thought you did a great job as always. And
Thank you.
I mean, once again, the whole purpose of this is to allow engineers and designers to make decisions up front, so you don't have to make downstream. You see, corrections need to be made, and then you go back to the drawing board. And it's funny. Last year I was at the PTC LiveWorks event, and I was talking with someone, and they said, it's interesting with they're explaining about their company. They said, it's interesting how sometimes there's never time to do it right the first time, but there's always time to fix it.
Yeah.
And it's funny because when you say like it's time to fix it, that means you're taking probably 3 times as much time to fix a problem than it is to, fix it in the beginning or prevent it from happening. So it's kind of interesting. Like we understand that, we see with our clients, people are busy. They need to get new products out the door. They need to get through the product development process. But a little bit of prevention up front saves a lot of time and will help you get those new products out the door faster. So if you have any, I'm gonna sorry to get tongue tied there for a second, but I'm gonna have this webinar posted to our YouTube page and the recording sent out either later today or tomorrow morning. If you have any questions or need any additional information, just reply to me by responding to the email invitations that were sent. So Andrea, once again, thank you very much for a great webinar, a great overview and very informative. And we will hopefully see you next week for our change management webinar for Windchill, or we'll see you the following week for another webinar in our Creo series.